Alrighty, let us go ahead and get started. So today we are going to continue our discussion on electric forces. Last class, we introduced the theory, and what we said was with electricity, you have two charges. You'll have positive charges and you'll have negative charges. Q, of course, stands for charge. There's positive and there's negative. And what we know is that when you have two charges near each other, let's say, they will apply forces to each other, or a force, let's say. And which direction the force is applied depends on the arrangement of the charges. So for instance, if you have two positive charges close to each other, they're going to repel each other. Whereas if you have a positive and a negative, they'll attract each other. And so the direction of the force depends on whether they're like charges or unlike charges. However, the magnitude of the force, how big the force is, doesn't care if they're positive or negative charges. All it cares about is what are the charges, that is how big, like how strong are the charges, let's say, and how far apart are they. And so the equation for the force felt by a charge due to another charge is given by F sub C, where C stands for Coulomb force. This just labels which type of force. It's not gravitational. It's not any other kind of thermodynamic or anything like that. So the force due to electric force charges is given by K times Q1 times Q2 over R squared. And K, of course, is a constant, and it's 9 times 10 to the 9th. Okay, and this number basically is there to try to fix the fact that we use human units rather than some universal set of units. And this K can change if you go into this field further and further. You may want to study what are the forces on charges which are in a piece of glass rather than are in a vacuum, or in water, or in a metal. And whenever these charges are in materials, well, the material's properties may affect how the electric force can pass through the material. And so depending on what material we use, we may have to adjust this number for K to get the appropriate results. However, for our purposes, obviously, we're just going to pretend like these charges are in a vacuum. They're not in a material. And so we'll use the value of 9 times 10 to the 9 always for K. And then we notice, of course, the fact that the force is a vector. Just as was true in first semester physics, it's still true today in second semester physics, that forces are vectors, because you can have a magnitude of the force and you can have a direction for the force. I push you with a force of 100 pounds, but do I push you to the right? Do I push you to the left? Do I try lifting you? Which direction am I applying this force? Forces are vectors, magnitude and direction. And thus, when you have an arrangement of charges, it may be necessary, depending on how they're located with respect to one another, it may be necessary to not just be able to add up the forces in particular, just like numbers, but rather like vectors. And we remember, when you're working with vectors, generally speaking, they're going to be pointing in different directions. And so if you want to add up the vectors, you have to do the component pieces. For this pair of charges, charge 1 to charge 2, there'll be an X component and there'll be a Y component for the force. And then for the next pair, for charge 2 and charge 3, he'll have an X component and a Y component for his force. And then for the next pair, charge 2 and charge 4, and so on. Once you've broken the components down, You add all the x components together and you get a final x component. Add all the y components together, you get a final y component. And then we remember, this is just the mathematics of it. Once you have your x and y, your final x and y components, then you can get magnitude and direction. And so that's basically what this process is going to be like. The physics of it is setting up the problem initially. What is the equation we're going to use? Can we calculate the x and y components of these vectors appropriately? The rest is just the mathematics. Following the steps of how to add vectors together, you get the final result at the end of the day. So that's what we discussed last time. And I believe I left you with an example to try to work out yourself, which is what's pictured here. You have three charges, Q1, 2, and 3, arranged in this fashion. And the question was to try to calculate the total force felt by charge 2. And so now I'll go ahead and do it myself. That way, under the assumption everybody followed my advice and tried it themselves, you'll be able to check your answer. So given a problem like this, how do I go about solving it? Well, firstly, I say Q2 is this charge right here, the top right corner of like a square, it looks like. He's going to feel two separate forces. So if I want the total force felt by Q2, it's really two different forces that I have to add together. Q1 will apply a force to Q2, and Q3 will apply a force to Q2. So if I add those, or if I calculate those forces separately, I'd get some number for each force. Then to get the total force, it's a simple matter of just adding those individual forces together. Thankfully, that's what works. It could have been that we live in a universe where this doesn't work. But this particular method is what's called the superposition method. If you have multiple phenomena all occurring on the same object, and you want to know what's the total effect on this object, there are some times where it's possible to figure out the effect by considering each phenomenon one at a time, as if they're the only thing happening, and do it for each set. And then once you've gotten each set individually, just add them all together to get the total influence. But like I said, this isn't always true. Sometimes you have to have a more complex way of figuring it out. Thankfully, with this particular topic, we don't have to worry about it. So if that's what I'm going to do, I'm going to figure out what's the force, for instance, what's the force on 2 due to 1. And I'm going to add it to the force on 2 due to 3. That's all I have to do. That gives me the total force felt by Q2. Okay, now that's a simple equation, obviously. And the details of it are going to be a lot more messy than what that looks like. But that's basically, in my mind, what I'm thinking. From here, what I do is I look at the picture, or if the picture is not drawn, then I draw it myself. And I try to figure out what will be the direction of each force. So I look at the force that charge 2 will feel due to 1. And I forget about 3 altogether. Pretend he doesn't even exist. So Q1 is a positive charge, and Q2 is a positive charge. Since they're like charges, I know that they're going to repel each other. And of course, that means that the force that Q2 will feel because of Q1 will be a force pushing him away from Q1, which means he'll be pushed to the right. And then, now that I know that, fine, I'll leave that alone. And now I look at what will be the force that Q3 will apply to Q2. And now I just ignore the fact that Q1 is there. I'm only looking at 2 and 3. And so 2 is a positive charge, 3 is a negative charge. Now, of course, I have 2 charges which are unlike opposite charges. And I know that unlike charges attract each other. They try to get closer. So that means Q3 will apply a force trying to bring Q2 closer to Q3. So he will feel a force down towards Q3. Okay. And so those are the two forces I have. Q1 acting on Q2 is some force, which I'm going to calculate, which pushes him to the right. And then Q2 will feel a force due to Q3. I'll calculate what his value is, but I know his direction is to try to move him downwards. And so I know overall, he's going to have some force, which is kind of down and to the right. Something like that. That's going to be the total effect that I'm going to expect. Now, I don't know exactly how much. I don't know if it's more down than up. I mean, more down or more to the right, I should say. But it's something down and to the right. Fine. Next step is now I start to try to calculate the actual values of these forces. So for each one of these two forces, the force that 1 does and the force that 3 does, I'm going to have an X component and a Y component. So I'll say, okay, let's look at the X component of 2, 1. Well, the X component, fine. Well, 2, 1, what's his equation? Of course, it's K, Q1, Q2 over R squared. And this is going to be in the X direction only. So generally speaking, I may have a problem which deals with angles. In this case, of course, I can see Q1 and Q2 are perfectly in line horizontally. So the total force is going to be an X component and Y component will be 0. You can look at the picture and see that. But as a general problem, which you would get next year when you do general physics 2, we may have it where we're actually looking at what happens to Q3. Well, the force that Q1 does to Q3, notice, would be this angled direction, up and to the left somewhere. And in that case, when you do the X component and the Y component, you may have cosines and sines of angles and stuff. But here, for this specific example, it happens to be that the X component is the total force, and for 1 and 2, and the Y component will be 0. But I still label it as if trying to remind myself I'm only looking at the X direction right now. All right, now we plug the numbers in. K, of course, 9 times 10 to the 9. Q1, remember when plugging the charges into this equation, I always plug in the charges positive. Whether the charge is a positive number or a negative number doesn't matter. You plug the numbers in as positive numbers. We already did the work to figure out, will this force be a positive force or a negative force? That's the arrows I drew. I took the time to look at which direction the force is going to push. So if I plug all the numbers in as positive, I'm going to get a positive answer. But if it should be pointing to the left, I just stick a negative sign in front of it. Okay, so it's important to not put negatives in with the charges, even if the charges are negative charges. Plug them in positive. The negative or the positive part of the answer comes at the end after you've already looked at the direction of the force and figured out, should it be negative or positive? The math won't tell you, the picture or your intuition tells you. So Q1, 1 microcoulomb, and I know a micro means 10 to the minus 6. So it's 1 times 10 to the minus 6. Q2 is 3 microcoulombs, so 3 times 10 to the minus 6. All divided by R squared, where R is the distance from 1 to 2 in meters, and it happens to be 2 meters. So it's 2 squared. Then I put, is this going to be a positive force or a negative force? Well, I look at what I figured out the direction of the force to be. That's the blue arrow here. And I was told that force is going to be pushed to the right. To the right, of course, is positive. So this is a positive force. So I leave it positive. And then, as I said, if this were the more advanced class, where I have slightly more complicated questions, I would now say, how do I make this the x component? Do I have to use cosine of the angle or sine of the angle? Things like that. Here, of course, I look at the picture. Q1 and Q2 are horizontal. They're a straight line in the x direction. So it's already in the x direction. I don't have to do anything to this. It's already in the x. So there we go. Once that's done, I just plug my numbers into my calculator and I'll get an answer. So 9 times 10 to the 9 times 1 times 10 to the minus 6 times 3 times 10 to the minus 6 divided by 4. And I get a value of 0.00675. And all of this is the x component of the force that charge 1 applies to charge 2. It's just one piece of the many pieces I have to solve for. So before I move on, are there any questions about this particular piece? All right. Well, either I'm doing an excellent, masterful job of lecturing, or it's just really early in the morning and people don't really want to think about the Coulomb force at 9:30. So we'll see as the class progresses if more questions arise. So that's the x component. What about the y component? Remember, for each force, I need an x and a y. So I'll say, okay, force on 2 due to 1 y piece. Well, of course, the equation is going to be the same, only now instead of getting the x piece of that force, I'm going to get the y piece of the force. However, with this specific example, it's really easy. I know that the force that 1 will apply to 2 is purely to the right. There's no amount of the force which is up. There's no amount of the force which is down. It's all to the right, which means it's purely in the x direction. And if the force is purely in the x direction, then the y component of the force is just 0. So 0. Done. That was very easy. I wish they could all be that quick. And again, just to foreshadow next year, if I was looking at something else where angles are involved, I may have, something like cosine of theta here and sine of theta here. And so I'd actually get a number for the x and a number for the y. It's just that this particular problem was set up so it's a little bit easier, so we don't have to complicate it with the angles. We could do the same type of problem, but just look at the fundamentals of the problem rather than letting more of the math bog us down. And there we go. I've got the x and the y components of the first force done, finished. I now move on to the second one. So I leave charge 1 alone. He doesn't exist anymore to me. Now all that exists in this problem is charge 2 and charge 3. So I need the force on 2 due to 3 x piece, which of course is going to be the same thing, k q2 q3 over r squared x piece. And now I look at my picture for those two. Well, notice that the force on 2 due to 3, 2 and 3 are lined up in the y direction. They're lined up vertically, which means that the force that 3 will apply to 2 is either purely up or purely down. There's no amount of his force which is going to be to the left or to the right. Thus, the y or the x piece of this force, the x component of his force, is just 0. So I don't even have to make a calculation. Done, 0, finished. But of course, I need to move on and look at the force on 2 due to 3 y component. K q2 q3 over r squared y piece. I look at my picture. Yes, there is an amount of this force in the y direction. In fact, it's downwards. So I'm going to have to do the calculation. All right, well, if that's the way it is, let's do it. We say K, that's 9 times 10 to the 9, times Q2, that was 3 times 10 to the minus 6, times Q3, well, Q3 is minus 4 microcoulombs. But remember, when I plug all the charges in, I always plug them in as positive. So it's just 4 times 10 to the minus 6, not negative 4. All divided by the distance between charge 2 and charge 3, which is given as 5 meters. So it's 5 squared. Next, I need only the y piece of this guy. So if this were a complicated problem with angles, I'd be using sine of theta or cosine of theta to make this the y piece. Here, of course, as I said before, they're lined up in the vertical direction already. So the force is purely the y directional force. So the y piece is the whole force. I don't have to do cosine or sine. There's no angle there. So that's the whole force in the y direction. Last step, is this positive or is this negative? Well, I already did that work. That arrow is written right there. Because they're unlike charges, they attract each other. Thus, Q2 is being pulled downward toward Q3. Downward, of course, is negative. So I have to put a negative for this force. Now all that's left, calculate all those numbers. So I get my calculator, 9 times 10 to the 9, times 3 times 10 to the minus 6, times 4 times 10 to the minus 6, divided by 25, I get negative 0.00432. And now I have the x and y components of the force on 2 due to 3. And then at this point, all the physics is done. Okay, I did all the hard work. The rest is, if I'm comfortable with vectors, which is why we did the math review at the beginning of the class, or beginning of semester, I should say. The rest of this, you should just, crank it out like it's a machine. I have all the pieces I need. I did all the work up front. The rest is plug these pieces in to get the magnitude and direction. Before I do it, are there any questions about this or these X and Y components? Now, one thing I'll remark, because I've seen it in past semesters, is particularly with respect to the directions, whether these forces are positive or negative and things like that. Sometimes people will question, well, yeah, charge 2 is being pushed to the right because of charge 1, but charge 1 is being pushed to the left, and we're not putting anything about that in my problem here. Or the same goes for 2 and 3. Charge 2 is being pulled towards charge 3 downwards, but charge 3 is being pulled upwards. So how do I know? Do I use the down or the up? Because both directions are in that force. Well, the answer, of course, is the problem doesn't care what happens to 1, and the problem doesn't care what happens to 3. All I care about is what's happening to charge 2. So ignore which direction 1 is going to move. It doesn't matter to me. I may have a different problem or a part B or something that'll say, okay, now tell me what happens to charge 1. Then I worry about charge 1. But of course here, all I care about is what does 2 feel? 2 feels a force pushing him to the right because of 1, and a force pushing him down because of 3. And that's what I care about for my calculations. Any other charge, how they move or how they interact is immaterial to me. I don't care. I just ignore it until such time as a problem needs that stuff. But here I don't need it. All right, so now we have the X component and Y component of the first charge, the first force, I'm sorry, force on 2 due to 1, and the x and y component of the force on 2 due to 3. And I know my original equation was, if I know F21 and F23, I add them together to get the total force on 2, which is what I want. So the rest of this problem is, here's two vectors, vector A and vector B. I gave you the x and y components of these vectors. Add vector A plus vector B to give me vector C. Magnitude and direction. That's all this is from now on. I've got these four numbers, they're four components, add the two vectors together. So first step is the total force on 2 x piece is going to be the force on 2 due to 1 x piece plus the force on 2 due to 3 x piece. Right? The total x component is just the sum of all the x components added together. So I look in my problem, I got 0.00675 plus 0. Well, that's easy, 0.00, that's a point, not a negative, 0.00675 is the total x component. And of course, the total force on 2 y piece is the force on 2 due to 1 y component plus the force on 2 due to 3 y component. And what do I have for this? Well, the force on 2 due to 1 was 0, plus the force on 2 due to 3, that's not a 5, it looks messy, is negative 0.00432. So I add those together and I get minus 0.00432. So there we go. I now have the total x component and the total y component. Last two steps. Find the magnitude of this vector. Well, I know the magnitude of the vector is given by the square root of the x component of the vector squared plus the y component of the vector squared. Remember, that's Pythagorean theorem, a squared plus b squared equals c squared. I have the x piece, which is the a, the y piece, which is the b. Take the square and take the sum of the squares, and that'll give me the square of the magnitude, the hypotenuse. So I take the square root of both sides, that's why the square root is there, and I'll get my answer. Very nice. So square root of 0.00675 squared plus negative 0.00432 squared. Now get my calculator out. 0.00675 squared plus negative 0.00432 squared. And remember, negative is in the parentheses, so the negative will get squared and become positive. Be very careful about that. And I take the square root of that, and I get a total answer, a magnitude of 0.008. And that's going to be newtons, because this is a force. There's my magnitude. It'll always be a positive number, because obviously you're taking the square root, plus or minus. But we always have the positive because this is magnitude. How hard am I being pushed? 0.008 newtons. The direction comes later. So positive number. Any questions on getting the magnitude of the total force?
I don't have a question about that, but I was wondering if you could scroll up just a little bit.
Yeah.
I had a question. So I understand how you got times 10 to the power of 9. How did you get times 10 to the power of 6?
Okay, good. So as a general rule, if you like with units, generally speaking, we have the main unit, which is meters, let's say. And then we have, as we go smaller and smaller, we have decimeters and centimeters and millimeters and so on. Well, there's two here we always skip. We never talk about them. And so that's 1, 2, 3, 4, 5. Then there's micrometers. Then we skip 2, and there's nanometers. And we skip 2, and there's picometers. And then going bigger, the same type of thing happens. There's kilometers over here. You skip those. Megameters, and so on. Well, micrometers sitting right here, or micro, and whatever the unit is, in this case, it's Coulomb. If you look, this is times 10 to the 0, because it's the unit. And 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, minus 4, minus 5. Here's 10 to the minus 6. So when you look at the charges I put in my problem, usually what you'll see, because people don't like writing scientific notation very much, is they'll just say 3 microcoulombs. Just like if we're talking about a distance and I say, oh, it's 20 centimeters thick. Well, centimeters is a bad unit. I need meters for my calculations. And so I have to convert. And usually you'd say, oh, well, 20 centimeters is 20 times 10 to the minus 2 meters. Or it's 0.2 meters, in other words. Well, same thing here. Microcoulombs, that's bad units. I want coulombs. And what I know is that micro means times 10 to the minus 6. Okay, so it purely comes from the fact of what charges were placed in this problem. They happen to be microcoulomb charges, because that's usually like the realistic real world size of charges we may be talking about. And so since they're microcoulombs, I have to convert them to meters, and the conversion factor is 10 to the minus 6. All right, so does that make sense?
Yes, it does. Thank you.
Perfect, perfect. Any other questions about what we've done so far? We're almost done. We only have the direction left. All right, last piece, direction. In which direction will this force be felt? Or that is to say, you can think about it like saying, which direction will my charge move? Because if a force is applied to it, it's going to move in that direction. Well, we know vectors, theta, the direction, is given by the inverse tangent of the y piece divided by the x piece. Okay, well, that's easy. Inverse tangent of the y part, which is minus 0.00432, over the x part, which is 0.00675. And of course, before I do this calculation, I'll make sure I'm in degree mode, not radian mode. So I have minus 0.00432 divided by 0.00675. And then inverse tangent of that guy, I get an answer of negative 32.6 degrees. Now, before I actually box this answer, remember, when we deal with vectors, the direction part is kind of fickle. You may do everything perfectly right, calculate it out correctly in your calculator, and get an incorrect answer. Half the time, in fact. So before I box the answer, I see, does it make sense? How do I know if it makes sense? Well, I already kind of did it. If you remember on my picture, I said, I know the force is going to be pushing him to the right because of 1 and down because of 3. So overall, I should have a total force which is down and to the right, the yellow arrow there. Okay. And then I just say, well, is negative 32 down and to the right? Yes. Negative angles just means it's this amount below the x-axis rather than above the x-axis. So there we go. It matches. I'm good. A second way of doing it, if you didn't draw it out on your picture like that, is you look at these components here, your final x and y components. And you say, which direction will a vector with these components point? Well, if I were to draw this out, I'd say the x piece is positive, so somewhere to the right. And the y piece is negative, so it's somewhere downward. So the arrow should be something like that. Now that I know in my mind in which direction this arrow points, down and to the right, I look at my angle. is this answer down and to the right? If it is, perfect. You do nothing, you box your answer. If, however, it didn't match, let's say the arrow should have been up and to the left, but when I get my answer like this, it's down and to the right. Now they don't match. If they don't match, you add 180 and then box your answer. So that's the two ways it can happen. Either the direction you get from your calculator matches what your intuition says, the same kind of direction, down and to the right, up and to the right, whatever. Or it doesn't match, in which case you add 180. Here they happen to match, so I'm good. I can box my answer. And that's it. What's the magnitude and direction, or what's the total force felt by charge 2? It's a magnitude of 0.008 with a direction of -32 degrees. Now, how did I do it? Walk through this once more. First thing I did was, of course, I have my picture drawn. And so I'll look for each force individually, which direction will that force point? Because that's going to give me some information later on. It's going to tell me if the components are going to be positive components or negative components. And then perhaps it'll also help me with the final angle calculation at the end. So here I looked, charge 1 and 2, forgetting about 3, just looking at 1 and 2. They're both positive, which means they're like charges. Like charges repel. So that means charge 1 will push 2 away. And in this case, that means he's being pushed to the right. So that's my blue arrow. Then forget about charge 1. I'm now looking just at 2 and 3. Well, charge 2 is positive charge. Charge 3 is a negative charge. They're unlike charges, which means they will attract each other. So that means charge 3 will pull charge 2 downwards towards him, which means the force on 2 due to 3 is downwards. And then, because I can do this with my intuition, there's only 2 forces here. I know that the total force is going to be something down and to the right. If there were 3 or 4 charges here with a whole bunch of different forces, it may not be so easy to figure out the total direction. But here I could do it, so I did it. That's what my yellow arrow is. The final answer should be something down and to the right. All right, so I leave that stuff alone. How do I actually do my calculations? I say, well, if I want the total force on 2, it's going to feel a contribution due to 2 other charges. There's going to be a force on 2 due to 1, and then there's going to be a force on 2 due to 3. If I could calculate those 2 forces individually, and then add the 2 forces up, that'll give me the total force. So I look at the force on 2 due to 1 first. I say this force can have an X component and a Y component because we're dealing with vectors. So the force on 2 due to 1, forgetting all about 3 doesn't exist. Well, of course, we have an equation for the force on 2 charges. So I plug my numbers in for those 2 charges. Remember, all the numbers are positive here because I'm going to put the negative or the positive afterwards. And then I have to make sure that if I'm looking at the X component, I'm only calculating the X piece of the force. In this case, because charge 1 and 2 are already lined up horizontally, I know the total force is the X component. There's no Y component of that force. So the Y component is easy. That's 0. I don't even have to do a calculation. The X component is whatever this equation tells me. I don't need a cosine, a theta, or anything here. So I plug my numbers in. I say, is this component a positive one or a negative one? Well, that's what my blue arrow told me. Q1 pushes Q2 to the right. In the X direction, to the right is positive. So he's going to be a positive answer. From there, I plug it in my calculator, I get a number. There's the X piece, and there's the Y piece for the first force. I do exactly the same process for the second force. Here's his equation. I want the X piece of him, but I notice that 2 and 3 are lined up vertically, which means the total force for 2 and 3 is purely in the y direction. There is no x component of that force. So the x piece is 0. The y piece, however, I do need to calculate. Again, I plug all my numbers in as positive numbers. I need the y component. In this case, the y component is this number. I don't need sine theta or anything. And then, is he positive or negative? Well, I did that at the beginning. Q2 is being pulled downwards, and in the y direction, down means negative. So I put a negative sign on him. Plug it in my calculator, I get an answer. There he is. From here, I've got the x and y pieces of every single force in my problem. Now, add up all the x's together, and I get a total x. Add up all the y's together, and I'll get a total y. The last piece, which is what the answer is what I want, magnitude and direction. Magnitude, you take your components that you just calculated, the final components, and it's the square root of the x component squared plus the y component squared. Plug them in, get an answer. There's the magnitude. This is always going to be a positive number. Last part, the direction. The direction is given by the inverse tangent of the y component over the x component. Plug those numbers in, get an answer. However, before I box that answer, this is the tricky one, I go back and I say, what should be the direction? And so at the very beginning, I did it. I said, well, because there's a force to the right, there's a force down. So the total force is down and to the right. Or if I couldn't do it, because it was a more complicated problem, I just look at these final x and y components. The final x component is something positive, so it's something to the right. And a final y component is negative, so it's something downwards. So my final vector is something down and to the right. I look at the answer that my calculator gave me, negative 32 degrees. Negative 32 is somewhere in the fourth quadrant, which is down and to the right. Because they match, this is right. I don't have to mess with it. I box it. If it happened to be something else, if this should have been up and to the left, but I get negative 32, which is down and to the right, they don't match anymore. So I'd have to add 180 to that answer. And with all of that, I now have my answer, magnitude and direction of the total force. Okay, so it's a big, long trial of stuff, a whole bunch of steps. Each step, however, is fairly intuitive. It's not that big of a deal. If I want the total force, add up all the individual forces. Okay, well, unfortunately, these are vectors, so the act of adding the individual forces is not straightforward. So I follow my vector rules. Find the x and y component of each force. Once I have all the x and y components of every single force, add up all the x's, get a final x. Add up all the y's, get a final y. Then I do magnitude and direction. All right, so with that, are there any questions about this? If you can handle a problem like this by yourself, you get a blank sheet of paper and you work it out, then any problem I give you on a test, you're going to be able to handle. The fact that there's 3 charges here and they're arranged in weird ways, and we have to do vector stuff, that makes it fairly complicated. Now, of course, we could get more complicated. If I were to ask you what's the total force on 1 or what's the total force on 3, this is more complicated. Because now all of a sudden we're going to have angles involved and the x and y components have cosine theta, sine theta stuff. It's going to be the same process. However, finding the x and y pieces are not as easy as, well, the x is the force and the y is 0. With those other questions, now you actually have an x component and a y component that you have to calculate. But for this course, we're not going to get there. We're doing it this way. All right. Here's an example I want you to work on. I'll let us off early today, but you have to, at least by the honor system, attempt this particular problem yourself before the next time we meet. And it'll be the last example, the last piece of electric force problems. From here, we're going to move on to circuits. Okay, but here's the example I want you to try. Let's say we have a charge, Q1 is 2 microcoulombs at the origin. And then there's another charge, Q2, which is 4 microcoulombs. And he is placed 10 meters away. Okay. The question is, where should I put Q3, which will be a charge of -3 microcoulombs? Where in between here should I place this Q3 such that the total force on 3 is equal to 0? Now, I put Q3 up in the air here, but really it's somewhere on the x-axis. Okay, so let me not confuse matters. It's going to be somewhere on the x-axis, not somewhere up above the x-axis. Now, where will it be? Maybe straight in between the two charges, maybe closer to one charge than another. I'm not sure. That's actually the point. The question is, where should you place Q3 such that the total force felt by Q3 is 0? And when I say where, what I mean is how far from Q1, okay, rather than how far from Q2. Yeah, go ahead.
So for this one, we would be looking for, actually, we would have our force would be 0, right? But we'd be looking for R.
That's exactly right. Yeah. The way you want to go about handling this type of thing is, first of all, we don't need X and Y components anymore. Everything's lined up in the X direction. There's no Y stuff. So everything's X stuff. So perfect. We're going to do the exact same thing. I know the total force 3 is going to be the force on 3 due to 1 plus the force on 3 due to 2. But now I know that whatever it is, it's equal to 0. So this is going to be my equation right here, this part. I don't need to know what the total force on 3 is like I did for the previous example. Now I know what it is. It's 0. However, now what's going to happen is when you plug your K, Q1, Q3 over R squared, and K, Q2, Q2, Q3 over R2 squared, whatever his R is, equal to 0. What you're going to see is this and this will be unknowns. We know the Q's, we know K. What we don't know is this distance. Now, at first, it looks like we have two unknowns sitting here, right? We don't know R, let's call it R1, which is a distance from 1 to 3. And we don't know R2, which is a distance from 2 to 3. But really, what we can do is be fancy. And this I need to show you because very few are aware of this trick. But when you get a problem like this, where you're going to place something somewhere to balance it, and you have two different distances in your problem, the distance to one object and a distance to a separate object. At first, that's two different distances, so it's two unknowns. But I only have one equation. Two unknowns with one equation is bad. So I have to convert these distances, so there's only one unknown sitting there. And the way you do it is you say, look, choose a place to put your Q3. There he is. That's where I'm going to place him. Where that is, I have no idea. That's the point of the problem, figuring out what this point is. But what I know about the point is that I'll call from 1 to that point, I'll call that R1. It's the distance from 1 to Q3. So that'll be whatever this number is right here. Call it R1. That's the unknown. But then what do you say about the distance from 3 to 2? What's this distance? Well, that's R2, of course, which is this number. But I don't want to call it R2, because if I call it R2, it's a second unknown. So how can I figure out how to convert R2 from an unknown to something that's already known? And here's how you do it. You say, look, if I want to know the distance from 3, here's 3, to 2, here's 2, which I'm calling R2. It's the same as saying it's the total distance of 10, right? From 1 to 2, the total distance, but then I subtract off this much of it, right? So another way of looking at it is like this. If I want to know the distance from this point to this point, but what I know is the distance from here to here is 20, and the distance from here to here is 5. The question is, what's this distance right here? Well, if this distance is 20, and this much is 5, well, the whole of 20 minus this 5 sitting there gives me what I need, which is 15. Same thing here for R2. What I want is R2. What do I know? I know the total distance is 10 from the origin to Q2. But that's too much. All I want is R2. So I have to take away the piece that we don't care about, which in this case is R1. So that tells me R2 then is the full distance of 10 minus the piece we don't want, which is R1. Another way of saying it is R1 plus R2 must be the total distance of 10, right? And then I just solve this for R2. R2 is 10 minus R1. That's where it comes from. So this right here is the critical piece. Once I know this, that's what I'm going to put right there for R2, 10 minus R1. And now my equation will have only one unknown in it, R1. R1 will be the only unknown. All the Q's I know, K I know, the 0 on the other side I know. R1 is R1, which is what I want, and R2 is 10 minus R1. Well, 10 is just a number, so R1 again. And that's what you're going to do. You're going to do that. You're going to have a big, long equation. It's going to look messy, but R1 is going to be your unknown. The rest of the work will be the algebra to try to solve for this R1. Okay. What you may find is this might turn out to be quadratic equation. Okay, so maybe it turns out quadratic, maybe not. It depends on how I set up these numbers, but you might find it's quadratic. If so, quadratic formula, of course. But anyway, that's the point. Solve for R1. What should this distance, what should that point be such that these two other charges balance their forces on him? So that's your problem. That is your task, a challenge. I haven't done this myself for you yet, but that's the point of physics. The point of physics or engineering or anything else is I have a project. No one's worked on this project before. I haven't looked this up in a book. There is no textbook that shows me how to do this. I don't have a professor that's going to come and show me how to work out the problem, because if he could do it, he would have done it and he'd have his name on the paper or whatever. It's my job to do something no one has done, which in this case is this problem. Can I take all my previous knowledge and apply it to this problem and see if I could turn out an answer myself and make a contribution? This, of course, is at a lower level, a small example of that, but that really is, at the end of the day, what it is scientists do. So try it out. Take the time today or tomorrow or this weekend, whatever. Try to work this out. You may not get an answer, which is fine. Like I said, we haven't done it yet. Or you may get an answer, which is perfect. I'll do it myself. And we'll see how it goes. From there, Tuesday, our next class, I'll do this. And then we will start on to circuits. I'm thinking in the future, I'm trying to think of how far I want to get into electricity, because our first test, I don't want to give our first test till we've completed this full topic of electricity stuff. So because of that, if we're starting circuits next week, we can expect a general timeline for our first test will be, of course, not next week, maybe the Thursday after, depending on how quickly we could get through the circuits. Okay, so have that expectation. Our first test will not be next week, but maybe the following. And then if we need to take a little bit more time, then it'll be the Tuesday after that, something like that. So just so you have kind of a feeling of when our first test will be. And of course, that test, the test, by the way, if I didn't say it earlier in the semester, it'll be online. I think everyone had me in the first for Physics 111. If you didn't, if you want to know how the test is run online, and of course, I'll discuss this when we get closer to the test, but just to allay any fears, I don't do the tests online like a timed test or like Canvas has the automated quizzes and things like that. But rather, I do my online test just like I do the homework problems. I will post something on the Canvas. It's a PDF file. It's the test. You work it out by hand, submit it back to Canvas, and I usually give the full day to work on it. That way, if there's any technical issues or anything like that, you're not getting kicked off the site because your internet went out and then you can't get back to the test or something. Or I give you the full day. That way, if you're traveling in a car or something and you can't actually take the test at 9:30, well, you could take it at 2 o'clock in the afternoon or 4 o'clock in the afternoon, whatever. So when the time for the test comes, of course, I'll go all over the details then. However, just so you know, that's how I run the online test thing, which is I post it just like I post the homework, and you'll have the full day to work on it. Anyway, with all of that rambling done, that's all I have for you today. So unless you have any questions for me, you are free to enjoy your weekend, and I will see you on Tuesday.
Thank you.
All righty then.